The project title is AES-128 Hardware or Software Code Design on SoC FPGA. So the course here is specified design and analysis of reconfigurable systems. So the team members are myself, Anil Shankar Saravana Sankar, and then Sujantini Manohar Nimmakumari. So the project overview is stated over here. So the FPGAs are widely used to accelerate compute-intensive and parallel algorithm. So this project implements AES-128 hardware or software core design system on an SoC FPGA platform. So HPS is the processor. So it is used for control and user interaction and software validation. And then FPGA Fabric, high performance AES-128 encryption acceleration. The goal is to demonstrate secure, correct, and efficient hardware or software integration using memory mapped interface. And then the objective of the project is to generate 128-bit AES key on HPS, accept 16 ASCII characters, perform software encryption and decryption on HPS as golden reference. Why AES on FPGA? AES is a compute-intensive and highly parallel FPGA acceleration, improves performance and scalability. So this is the overall hardware software system architecture. So here in HPS ARM processor, we have 128-bit key generation and then 128-bit plain text retrieval and then decryption and then IO control, which is mapped through AXI Lite memory into the FPGA fabric, which does the AES encryption. So the AXI Lite register interface. Input registers are plain text 128-bit and key 128-bit. So the control registers are responsible for the start of encryption. The output register is the ciphertext and status flag. So we are using QSys platform design integration and AXI Lite interface over here. So here, it is built in using the built-in Intel QSys. Then HPS communicates with the AES hardware via lightweight AXI Lite. And then AES module is exposed as an AXI Lite memory map slave. AES hardware uses an AXI 4 Lite slave interface, supports register-based communication between HPS and FPGA. The standard AXI signals used are address channels, AWAR, and then data channel, WWrite, W data, R data, which is like write data and read data, and then control and response signal, that is like valid, ready, and response, and then input register, which is like plain text and encryption key with 128-bit each. So control registers are used for like starting the encryption trigger, and then output registers, it's like ciphertext 128-bit and status flag. So here we can see clock 0 and AES AXI that is being created. So the clock input given here is clock 0 and then rest input. So all these things are given over here. So memory mapped register design. So AES hardware is exposed as a memory mapped AXI Lite slave. So HPS accesses AES register using 32-bit word addressing. So input registers, which is like of plain text 128-bit with registers 0 to 3, and then encryption key 128-bit registers 4 to 7, control register 8. So writing like 1 from 0 triggers the AES encryption as stated in the slide, and then the output registers read by HPS, ciphertext 128-bit, register 32 to 35, status register, register 36, finished 1 indicates encryption complete. So you can just see this table over here. It's like HPS to FPGA, HPS to FPGA. So the direction is mentioned in this specific table for each functionality. Okay. So the encryption pipeline is as stated. So the FPGA implements AES-128 encryption only. So the encryption follows the standards AES round structure, which has sub bytes, shift rows, mixed columns, add round key. A total of 10 rounds are performed. Initial add round key, 9 full rounds, final round with mixed columns. design characteristics, multi-cycle hardware implementation, controlled using an enable signal. A finished flag is asserted after encryption complete. The cipher key is 128 bits. Plain text is 128 bit too. Okay, so round 1, round 9, round 10. So HPS software golden reference validation. So here you can see user input is first given and then random key generation. Software A is encryption, which is like golden. Send to FPGA. Read HW ciphertext. Software A is decryption. Validation, which is like match or pass. HPS responsibilities runs AES control software on ARM processor, generates a random 128-bit AES key at runtime, and then this accepts up to 16 ASCII characters as plain text input. And then this communicates with FPGA using the AXI light registers. So yeah, the functionality and the flow is as follows over here. So we are looking at the validation result. So the top one, yeah, as you can see over here, right? It is showing that the plain text key is generated over here, and so this is like so showing the generated key plain text in both software and hardware ciphertext values. And then notice that the hardware and ciphertext matches the software ciphertext, confirming the correct encryption. The decrypted text matches the original output, validating the entire system. So that is the result over here. So you can see that um, FPGA synthesis result over here. The number of ALMs is 5937. ALUTs is as follows. Registers, IO pins. So these are the respective screenshots that were generated. Like this is the fitter resource usage summary. Okay. So this is the timing analysis and perform verification. Timing analyzer report path. The path delay is as follows, and then Fmax delay is given over here. So the conclusion is that we have successfully designed and implemented complete AES 128 hardware software. HPS handles control and key generation, user input, and decryption, while FPGA accelerates AES encryption. Communication between HPS and FPGA is achieved through memory mapped AXI light interface. Hardware encryption results exactly match the software golden reference. So here you can see challenges faced. And then the first one, hardware software data alignment, which is like the NDNS, ensuring consistent byte ordering between HPS software and FPGA hardware AES implementation. AXI integration correctly maps 128-bit plain text and key across multiple 32-bit memory map registers. Control and synchronization, which is like responsible for designing reliable start or enable finished signal between HPS and FPGA, and then debugging hardware and software mismatch, validating FPGA result against software golden reference, and resolving mismatches. So this is the conclusion of it. So end-to-end validation confirms correctness and reliability and integration of the system. So we have successfully performed the project, and thank you.